finishing this lesson. Here we go. All right, where we left off. Why in anyone's right mind would they do all this work, simply for an approximate answer, which was the 0.7108, when in a couple seconds they could run a binosum program or any other binomial program and get the exact answer in a fraction of the time? That is a wonderful question, which will be answered actually right now. I'm going to scroll down to the bottom of this sheet. When there are roughly more than 400 trials, when n is greater than 400, your calculator, as powerful as it may be, does not have enough memory to add up all of the things you need to add up. So say I had 500 trials and I want to, actually, better yet, let's do number 4 right now. Let's go out of order. In 1,000 tosses of a coin, so n is 1,000. Find the probability of flipping between, it's not 400 and 600. I made an error. I want to, let's say I want to flip between 480, and 520 heads inclusive. All right, so I'm going to edit that. All right, so I'd have to add up, your calculator would have to add up actually, let's do that right now. Let's run the binosum program. Binosum program. So probability of flipping heads is 0.5. Trials, type this in, is 1,000. The high successes, well, it says between 480 and 520, so 520 would be the high successes. The low successes would be 480. I'm going to give you a moment to run your binosum program and see what it says. All right, pause the video and run it. It should say error overflow. And that's after trying to chew up the answer for a while. The problem is binosum does not have your calculator does not have the memory to add up all of those potential binomial probabilities individually and add them all up. So there are some cases where you have to use the normal approximation to answer a binomial question, and this is one of them. So first, let's find the mean and the standard deviation. So the mean of this would be 1,000 times 0.5, which is 500 heads, which makes sense. Flip a coin 1,000 times, you would expect 500 heads. Okay, the square root of 1,000 times 0.5 times 0.5. Plug that into your calculator, and you should get an answer of 15.811. 15.811. Remember, round all standard deviations to 3 decimal places. So in the middle of my normal curve, I'm going to put 500. I need to find the probability of getting between 480 and 520 heads. But remember that we're approximating a binomial answer with a normal curve. So I'm going to draw little histogram rectangles around 480 and 520. This word inclusive is very, very, very important because I need to include the 480 and I need to include the 520. So if I am shading in between here and I want to include both of these numbers, I have a choice. I could either start at 479.5 and shade to the right, or I could start at 480.5 and shade to the right. If I want to include the 480 as I shade to the right, I'm going to start at 479.5. What if I did not want to include the 480 as I shaded to the right? What if the word inclusive was not there? Then I would start at 480.5 and shade to the right. Do you follow? All right, I also want to go to 520 and include 520, so I'm going to go up to 520.5. These are my raw scores. I now need to convert them. Oops, what happened there? I now need to convert them to z-scores. All right, so the z-score of 500 is 0. If I take 520.5 minus the mean of 500 and divide by 15.811, I get an answer. Okay, and that answer is 1.296. So that would round off to 1.296 would round off to 1.30. That is my z-score. I don't know if you realize it, but 480 and 520 are equidistant. So if I did use 479.5, I'd get a z-score of negative 1.296 or negative 1.30. So negative 1.30. All right, and so I need to look up 1.30 on my z-table. And what do you get when you look up 1.30 on your z-table? You get 0.4032. And you also get 0.4032 here. A picture is worth 1,000 words. Add them together, and you get 0.8064, roughly 80% of the curve. So here was a perfect example of a problem where I could not use my calculator to answer a binomial question. I couldn't use binosum. There were just too many trials. So I have to use the normal approximation. So reminder here, when you use the normal approximation, you need to find the mean. You need to find the standard deviation. And most importantly, after you draw the numbers in question, you need to do a 0.5 adjustment on the numbers that you're working with. This is only when you're answering a binomial question with a normal curve. You have to do that 0.5 adjustment, also called the continuity correction factor. All right, so I'll leave that right there. Pause the video, replay it, take this in. The homework is just like that. There's one other piece to this lecture that I want to bring up, and it was actually last night's homework, and it's what I promised you would be on this lecture. All right, it says, notice that if we take the histogram, we connect all the midpoints here, and I connect the midpoints, what I get is a nice smooth curve. All right, but it is an approximation, and if you're really curious about it, the approximation is just this. Notice that at some places, I am underestimating the curve, but in other places, I am overestimating. How about that for color? That's so cool. All right, so between those underestimates and overestimates, it turns out to be a nice approximation, but only under certain conditions, and these are the conditions that need to exist. Okay? These are the conditions that need to exist. So I'm going to scroll down, and it says, notice from example 1. So in fact, and this is the big thing right here, okay? If n times p and n times q are both greater than or equal to 5, the binomial distribution can be approximated by the normal distribution accurately. All right, so it's a suitable approximation. However, if p is 1/2, this rule can be violated. We'll get to that in just a second. So let's go through this homework right now and answer this. If p is 0.2, that means q is 0.8. So n times p is 10 times 0.2, which is 2. N times q is 10 times 0.8, which is 8. All right. Are both of these numbers greater than or equal to 5? No, this is greater than or equal to 5, but this is less than or equal to 5. So guess what? From last night's homework, determine if the normal approximation would be suitable. Would the normal approximation be suitable in A? No, it would not. And just for proof, the graph of this particular curve right here would look skewed. And just pointing it out right now, this skewed graph would look like this. Just very quickly. What if I overlaid a normal curve on top of this? Does it match? No. Normal approximation is not suitable. How about 18 and 0.9? All right, so that means sorry, just looking over something right here, q is 0.1. 18 times 0.9 is 16.2. And 18 times 0.1 is 1.8. Both of these numbers are not greater than or equal to 5. As a matter of fact, this one's not. So no, once again, not suitable. This one right here is very much skewed to the right. A normal curve would not overlay. All right, how about 40 and 0.4? I think we might have it here. All right, n times p is 16, and n times q is 24. All right, by the way, this is 0.6. Histogram looks fairly symmetrical, and the normal curve overlays it very well. The answer to C would be yes. As long as n times p and n times q are both greater than or equal to 5, it works. Now, here, n times p and n times q are 4 and 4. They're not greater than or equal to 5. This is where this little corollary comes in, because if you drew a histogram, it would be very much symmetrical. As a matter of fact, this is the first example in our notes, and it overlays it very well. So the answer here, even though NP and NQ are not greater than 5, that works. I'm going to cut off this video now because I've got 3 seconds before 10 minutes.